George. Today we want to talk about a weird concept called periodicity. What's periodicity?
When you look on a periodic table, that's the name,
Periodicity, periodic table. Oh, it's like
There's
work together.
There's a connection there. And the idea is that there's trends.
Yeah.
If you go across the periodic table or down the periodic table, you're going to see some repetition of trends, which is actually how they put the periodic table together. So we call that periodicity. And there's three main trends that we want to talk about today, right?
Let's talk about the first one, which has to do with atomic size.
So atomic radius, we'll call it.
Yeah, radius actually. So it's the radius of an atom. So you know what think of an atom as a sphere, and what is the size of the atom? And we measure it by the radii of that atom.
Now, not to get too confusing here, but because electrons are moving a lot, this is not a set distance, but we can look at the periodic table and kind of determine whether or not one atom is bigger than another one.
So now it makes sense that heavier things are bigger than lighter things. So as I go down the periodic table, like let's say in column 13, boron weighs 11, aluminum 24, 26. As I go down, they get bigger, right? Is that correct?
Yeah, but we want to be really careful about using mass because the reality is we really care more about the
Size.
energy levels and the size. So as you go down, remember we did this in the last video, as you go down, we go down different energy levels. You can even take a look on the side here. It goes 1, 2, 3, 4, 5, 6, 7. Those represent energy levels. So if I were to compare...
The energy levels are in different shells that are further and further away from the nucleus.
So if we take a look at this atom right here, right? Let's make this lithium, right?
Right.
So lithium has a nucleus, has 2 electrons in its inner shell, and it has 1 electron in its outer shell, right? But if you take a look at between lithium and sodium, the only difference between these two is that sodium has its outermost electron in the 3rd energy level.
So actually the first 2 levels, there's 2 electrons and then 8 electrons, right?
Yeah.
In the second level, and then we've just got 1 baby electron in the outer shell. So it makes sense that as you go down, you add another shell. When you add another shell, the atoms get bigger.
So we go from an atom that looks like this to an atom that looks like this. Shows the masses here.
So if we look at lithium weighing 7, beryllium 9, boron 10, 12, again, you would expect them to get bigger as you go across, and that doesn't happen. They actually get smaller.
That's true.
When you go across the periodic table, they get smaller. Now we have to explain why.
So this is probably the harder of the things to explain, because if we just take a look at any particular atom, let's say we take a look at
Let's go like sodium to
sodium,
magnesium,
right? So would you agree with me that sodium typically has 11 protons and it has 11 electrons?
Yeah, of course.
But of those 11 protons, 11 electrons, there's only one electron that's in the outer shell.
One baby in the outer shell.
So we're going to pretend here that the outer shell is all we care about. So we have 1 proton and we have 1 electron that match up.
Right, because the 10 cancel out.
Yeah. Now, this 1 electron is only going to feel the pull of 1 proton, right?
Makes sense.
But if we go to the next atom, which is magnesium,
which has
it's gonna
12 electrons.
It's going to have 2 protons. I'm going to write them like this: 2 protons, and it's going to have 2 electrons in the same energy level. Now watch. This electron right now feels the pull of 2 protons. So this is being pulled in more tightly than this is. Now this one here also feels the pull of
both of them.
Of both of them. So the net result is this: if I was pulling on you versus 2 of me pulling on you, you're going to get pulled in a little more tightly.
Right. So this atom is going to have a diameter, let's say this, and this one's going to have a diameter just a little bit smaller, if you will, or a radius.
And if we were to recreate this, there's an electron here and a proton here. Here we have 2 electrons and we have 2 protons
and that is what's pulling it in. So as you go across the periodic table, because what's happening, and there's a fancy term. What's the fancy term?
We call this effective nuclear charge, which is a crazy term.
Not everybody understands. That's the fancy term. That as you go across the periodic table, they get smaller, and as you go down, they get bigger. So maybe we can. What I'd like you to do in your notes is to sketch a periodic table, and this is going to be just total nasty sketch here. And what you're going to do is you're going to say, for the largest one, so as you go, let's talk about getting bigger, right? So we just talked about as you go across, they get smaller. But as you go this way, they get bigger. And as you go down, they get bigger. So if you think about it, who's going to be the biggest bad boy on the periodic table?
Oh, it looks to me like it'd be francium.
Francium. So francium is the biggest atom, and then conversely, which element would be the smallest bad boy?
Well, you're looking all the way up here in this upper corner to helium.
So and that's weird. Hydrogen weighs 1, helium weighs 2. But you said, no, it's not that way. He's the smallest element on the periodic table, where francium is the biggest.
Now, it is really important because We need to know atomic radius trend to be able to talk about all the other trends. It's kind of like if you're a Lord of the Ring nerd, you're going to realize that the one ring that rules them all, again, really nerding out here, atomic radius determines all the other trends, which is kind of weird. And also it's kind of a big deal because size matters, but not in the way you think. Here, it's really good if you're tiny. So the smaller you are, the more control you have over things.
So we've talked about the atomic size, but also we've been learning that atoms can be ions.
Right.
And so we want to compare an atom to its ion.
So we have cations and we have anions.
And cations, cats are good, right? An means negative, so positives are cations and anions are negative. So let's compare, like, say, magnesium and the magnesium ion.
So let's go magnesium. And magnesium, if you take a look at it on the periodic table, doesn't it have 12 electrons? Yeah.
But when he's an ion, his charge, when he's in column number 2, is positive 2.
So Mg2 plus, it would go
12 protons, tricky, 10 electrons.
Now here's the cool thing about this is that the protons are what are doing the pulling in, right? So these 12 protons, if they have to pull 12 electrons, that's gonna make them work harder than to pull in 10. So and just like dragging something. If you have to drag less, you're gonna be able to drag it better, right?
Yeah.
So here, these 10 electrons are gonna get pulled in more closely than these 12 will. So that means that
he's a smaller bad boy.
It's a smaller atom.
So maybe draw like a circle, like.
So this right here, if we're talking about energy levels here, and Mg has 3 energy levels, right? 1, 2, 3. Here's the difference between these two. This has 2 electrons in the outermost energy level. When we remove those, there are none in the outermost energy level. So in reality, this now becomes the size of the atom.
Quite a bit smaller.
And you can see how the cation is significantly smaller than that atom.
But with an anion, it's a little different ballgame. So let's take, say, fluorine and fluoride.
So let's take a look at fluorine again, if you want to flip across here.
Remove here. Fluorine is in column 17 with his 9 protons and 9 electrons.
So let's take a look at this now. We have fluorine with 9 protons. Well, that's a G. 9 protons and 9 electrons. And in order to become a full outer shell, it has to gain 1 electron to become F minus.
So it's actually going to be 10, because his charge is -1 when he's an ion. So it'd be 10 electrons.
And the same thing works, except it's a little bit different because here what we have is we have our 9 protons in the middle. And if you take a look with fluorine, there's 2 energy levels, right?
Yeah.
Well, there are 7 electrons in this energy level.
Right.
In the outermost.
In this case, it's the same ballgame, but you're going to have 8 there, right?
Correct. Now,
Because you added 1 electron.
let me ask you this. Is it easier to pull in 7 things or is it easier to pull in 8 things?
7, because 7. I got to fight against 7 guys instead of 8.
So that means that as you go here, that negative ion is actually going to be bigger.
So basically what you're going to find is that if this is the size of the fluorine atom with the 8 electrons, that's going to make it what?
Just slightly bigger.
Just a little bit bigger. Okay? The next trend we're going to talk about is something called ionization energy. Ionization. Think about that for a moment. We're ionizing, making something into an ion. And really this is the amount of energy it takes to remove 1 electron from an atom. Okay? And ultimately this comes down to the size. Who's holding on to the electrons the tightest helps you to determine who has the highest ionization energy. Now if you think about it, this comes back to the ionic size, or the radii that we talked about at the top of the video. And if we think about that, remember, who was the smallest atom that exists?
Well, I believe that we said it was helium.
Right, so it's helium, and so that means that the protons are super duper close to the electrons. So since he's so small, it's gonna be really, really hard to pull his electron off of him.
Correct.
Right?
So if I were doing this, and let's pretend we don't care about all the other electrons, but if I were to ask you, this is my protons pulling everything in, is it going to be easier to pull off this guy if you're from the outside pulling in, or this guy?
Well, clearly because these are closer together. He's holding on to this electron super tight, but this one he's not holding on very tightly.
I have an example that might help everyone out. So you know when you're out on the weekend shepherding, you have your flock wandering down the streets here of Houston. It's a dangerous task, but when the sheepses are in closer to you, you can protect them better. Yeah. If there's wolves running around, and again, you know the wolf problem we have here in Houston, a wolf is going to very easily be able to come and grab one that's like
on the outside.
On the outside, they're not going to come over and grab one that I'm like walking right next to me with my crook of hitting, right? Yeah. So the ones that are in closer, it's going to require that animal that wants to take it away a lot more energy or effort. And that's kind of how it works with an atom. If I have an outlier, one of my sheep is like, I don't really care about you, shepherd, and it's wandering away from me, I'm not going to be able to hold on to it or keep track of it as easily. It's going to be a lot easier for a predator to pull it off. Probably a terrible example, but...
So the trend pretty much continues because if we go back to our size thing, he holds on to it most tightly, and he's the smallest atom. The biggest atom, francium in the bottom left corner, holds on it to the most weakly, and so he gives up his electrons super easily. By the way, if you recall, when we blew up the pumpkins, right, we put in sodium so he's gonna have a low ionization energy, and he gave up his electron very, very quickly and very, very violently because he has a low ionization energy.
Now we need to be really careful. We're talking about this. If I'm trying to steal something from you, I'm not going to walk right up to you. I'm going to walk away from you and grab something that's farther away from you. So francium, it has 87 electrons. We're talking about the farthest electron from the nucleus, because the electrons that are close to the nucleus of this guy, they're going to be really, really hard to pull off. We're talking about this, and again, it makes sense, right? If I'm going to try and pull from you, I'm not going to run in there and grab an electron from the inside of you. I'm going to grab an electron way out here because you're not going to be able to, I'm off screen even, that's how far apart it is. So just be aware that when we talk about francium not being able to hold them as tight, we're talking about the outermost electron at the edge.
And we have one more trend to talk about, and this is a big fancy like $5 word called electronegativity. So electronegativity is the attraction of one atom for the electrons of another atom. But what does that mean?
Well, it simply means this. It's how easily or how able I'm able to grab an electron off of another atom.
And I like to call this like the strength of an atom. An atom who's strong can take away the electrons of another, right? So what's your sort of picture?
Do this for me. Let's pretend you have an electron. So that's the electron that I want to grab, right? And this is my atom. So here's my outer cell electrons, here's my nucleus. So right now, my nucleus is what's going to be doing the attracting.
Right, because this is negative and this is positive, so this is what's attracting and pulling.
So this right here is pulling that electron. Now, in which case is the atom or the nucleus can be more able to grab that electron? If the nucleus is right here in a smaller atom, or if the nucleus is over here in a larger atom.
Well, obviously, when it's further away, that's a longer force to attract, so I think it's got to be the closer one.
Yeah, so of these two right here, when we have a smaller atom, its electronegativity, which is how easily or how able an atom is to gain an electron, goes up. So that whole thing about knowing about atomic radius becomes a big deal, because the smaller you are, the greater your electronegativity is going to be. So if we go here across the periodic table,
the electronegativity is going to go higher. So you would expect, like atomic size, the smallest one would be the greatest electronegativity, but we sort of have a bit of a weird problem here.
Yeah, so this far column over here are the noble gases, and you remember my class, and we talked about it before. Noble gases, don't they have it set?
They're happy. They've got
They have full outer shells. Why in the world would they ever bother trying to gain electrons?
And they don't.
They don't. So when we talk about electronegativity, how easy it is to gain an electron, we don't include helium down below, so those kind of don't exist, which means therefore that fluorine is the most electronegative atom on the periodic table. In fact, if you're ever at a loss and you're like, I don't know which is more electronegative, just think of yourself as going like this. The closer you get to fluorine is the most electronegative, and that's going to determine how easily you're able to gain things.
Now let's summarize our trends for just a moment with some pictures, right? For electronegativity, if you go over and up, they get bigger, and these don't count. Make sense? For atomic size, so for atomic radii, what's the trend?
So as you go across and as you go up, you get smaller.
So maybe let's just make sure that we go higher. So if you go across and down, that's how you get the biggest. Maybe it says we'll go for the biggest number. The biggest number. And then the other one is ionization energy. And what's the trend with ionization energy?
It's exactly the opposite of atomic radius.
Yeah. So it's over and up. And then it does include the helium category. So these are the three periodic trends that we've learned about. Make sure you understand this, because you're often going to get questions like, rank these from lowest to highest, or highest to lowest in size or ionization energy, etc.
And we're going to revisit these two, actually all of these trends when we're trying to make molecules fit.
Yeah, this is actually kind of the beginning of what we talk about bonding and how things actually connect to each other.
See you next time.
See ya.